Welcome to qnawire.
Clay that is thrown at a stationary block. In this piece of clay, let's say it's moving with velocity vi, and it has mass m, and this block is big mass m, and it's again stationary. So the collision happens here, and then afterwards you have the clay block system moving together with a certain velocity v final here. And then they tell you that this thing just moves a distance d, and the surface has a coefficient of friction mu. So they want you to work all your way back to the initial velocity here. So the basic equations for momentum that we're going to keep track of are, so again, pi has to be equal to pf, because this is an inelastic collision, but momentum is always conserved. So the first thing that we want to do is work on the system here to find an expression for v final. So we know that the only thing that's slowing this thing down here is the frictional force. So we can use kinematics to try to find it, but what you notice is that kinematics usually will have a way to solve this problem, but it's easier to look at it from an energy perspective. So if you imagine this block has some kinetic energy, and over here it has converted all of the kinetic energy into some kind of heat caused by this frictional force. So this frictional force is the only force that is doing work on this system. So we can say that the change in kinetic energy is equal to whatever the work done by the frictional force. So the change in kinetic energy here, because it's v final to 0, is just going to be half. But this is the combined mass of the total system here, plus or times the v final squared. This would be equal to, so the work done is force, and the force here is the frictional force, which is mu, and the normal force. So it's going to be mu times a normal force. So this is the force, again, times the distance, which is d. But we can simplify this normal force further, because we know that the normal force is opposite the gravity for the system. So this is just going to be m plus m times g, and then again times d. So now notice you have masses on both sides, so these things can go ahead and cancel here. So you find that your v final, once you take the square root of both sides, is actually equal to the square root of 2 mu g d. So this is your final velocity. And once you have the final velocity, now you can work backwards. So this v here is 0. So the initial momentum is just mvi. This would be equal to the final momentum of the system, which is m plus m. And then we know that this was moving with the final velocity vf, which is equal to this. So this is now, so to find vi, you just divide by the smaller mass here, which is m plus the big mass over the smaller mass. So this is one term, and then you put in your final velocity, which is 2 mu g d. And that should give you the initial velocity, or a symbolic expression for the initial velocity.